Alright, so in this video, let's review again the concepts of sensitivity and specificity, but of course also type 1 error and type 2 error. And again, type 1 error is a false positive, which is like a person that's healthy is tested positive for, let's say, a disease. A type 2 error is like a false negative, meaning that a person that is actually sick is tested as healthy. And specificity, again in words, is the probability that, to stay in the context of like public health, that a healthy person is tested healthy or a true negative. And sensitivity, that would be a true negative, meaning that a sick person is actually tested correctly as sick. So now assume that people with a healthy heart have on average a BMI of 25 with a standard deviation of 25, and let's make that green. And people with an arterial disease, they have a BMI of 33 with a standard deviation of also 2.5, and let's make that red. So now assume that the person is initially considered at risk if their BMI is 30 or greater, and then they will be sent to further screening. Okay, so now what can happen is that people that are actually not at risk, they are being sent to further screening, which would be a type 1 error. But the first thing I want to do is I want to draw those two populations. And again, I know that the standard deviation is 2.5, and the healthy population, they have a mean of 25. So I know that roughly at 3 to 4 standard deviations below the mean, the probability curve approach the x-axis. So maybe what I will do is I will draw the x-axis with the BMI starting maybe at 15, and I go all the way to 43, which is another plus 10 for the second distribution, which is for the people at risk. Okay, so I start at 15, I highlight everything, I go to Home, Editing, Fill, Series, and again, to make the lines maybe smooth, I have a step value of 0.1, and I stop at 43. Okay, so now I have a column that starts at 15 and ends at 43. Now I add, so what I want to do is I want to draw something which essentially looks like this. So we have a distribution for the healthy, which looks maybe something like this, and then a distribution for the non-healthy, which looks maybe like this. And I also want to show somewhere that critical threshold of 33 at which people would get sent for further screening. Okay, so let's first draw the population for the healthy. And then we use again the formula norm.dist. So we use in Excel norm.dist because we have a normal distribution but not a standard normal distribution. Okay, so the healthy, I want to know, okay, norm.dist, open parentheses, and then I click on the BMI, and then that BMI comes from a population with mean 25 and a standard deviation of 2.5, And again, I want to draw the probability distribution, so it's not cumulatively, so I enter 0. Okay, let's copy down that formula. And now we do the same for, actually I don't like all those decimals here, so let me convert that into a format, cells, number 3, good enough. Then we have the at-risk population. And again, I use the formula norm.dist. Okay, so the 15 comes from a population where there's the mean 33, the standard deviation is 2.5 as well, and again, then cumulatively. Let's copy down this formula, and again, I want to format the cells as a number. Okay, so now at the value of 30, I want to have a vertical bar. So I only need to add a value at 33. Everything else is a number that's not available. So I call that threshold. And what I say is an if formula. I just say if the BMI is exactly equal to 30, which is the threshold value, comma, then just use the maximum value of the probability distribution functions, the PDFs. And now I have to fix that with F4, and that will make sure that I can get a vertical line which is as high as the peak of the probability density functions. Okay, and if the value is not equal to 30, well then just enter number NA, which is the numbers not available, and then close parentheses. So now I have only one value, and that should be at 30. So if we quickly go to 30, we can see, yeah, here we have 0.15 958. And because I want to show some areas associated with the type 1 error or specificity or type 2 error and sensitivity, I create here something that I call area, but I enter just initially everywhere number NA. And it will become clear later why I'm doing this, because I want to visualize something later. Okay, so now we have the data. And so what you see here, which I drew by hand, now we draw it now very accurately in Excel. So let's highlight the complete data array, and then we go to data, insert, and then recommended charts, and maybe look at all charts. Yeah, we can take this one, and then we have to change it anyhow. So I'll just quickly take this one, which is like a column chart, but it obviously doesn't look too nice. So we still need to format that a little bit. So I want to change that diagram, and there is the option, if you right click over the diagram, there is the option change chart type. Okay, I'll change it, and I want to change it to a combo. Okay, and I want the healthy not to be displayed as a column, but as a line. So I click and change that to line. And likewise, the at risk, they also shall be a line, but the threshold, that's actually a column. And the area, that actually shall be an area, so I click on area. Okay, so now we have our two distributions, and maybe we don't need a title, and we want to make the green, the healthy green. So I'll change the outline, make that green, and the outline of the healthy, I make that red. But maybe that's not good for the people that struggle with red-green color blindness. So I'll make it not red, I make it lavender. And then I want to make the threshold a little bit stronger. So I format this data point, and I click on the format bucket, and I put a border around which is really thick, maybe in black, and I'll make that 3 points thick. And the fill is a solid fill in black. And okay, so I don't know why. So I have to, so that in the legend, so that the threshold becomes black 2, I have to actually format the data series and change that to black. And what I also find useful here might be actually to add maybe vertical grid lines. Now it doesn't look too good, so we have to clean up maybe the x-axis a little bit. Make sure everything is on tick marks. We go to tick marks. The interval between the tick marks is 10. And the labels are also at 100 in this case. Okay, so this is now a much nicer diagram than what I drew here. So let me just erase again what I drew. Okay, so now that is something we can work with. So, okay, a healthy person has a probability of what % of being considered at risk. So that is related to the healthy population. And those are all the people from the green population, the probability to the right of the 30. So that's why I had another rubric which I called area. Maybe I'll make that now a little bit smaller. So that means I go to the 30, and then I say the area. Okay, so the area is, so the healthy people are in column B. So now I go to the threshold value of 30. And then if I want to illustrate the area for the type 1 error, I just pick up the probability value, which is here 0.22, and I highlight that one. So now that should be picked up in my graph, in my diagram. So let's go up again. And you see we have now the area shaded here in purple. Maybe that's not the best way to shade it. Maybe I would have to zoom in again. So let's give that another color, maybe a gray. And then we maybe fill it and maybe make it transparent too. Actually, we don't want to have an outline, so no outline. We just want to color it and make it maybe a little bit transparent as well. So, oops. So format data series. Solid fill, the gray, make it a little bit transparent. Okay, so now we can see it. So the area for a type 1 error is everything here to the right. And it looks like we lost now the format axis. So let's go back to the labels. And the interval is back to 10. Okay. So now it looks really nice. But what is that probability? So what we need to do is we need to ask, in the green population, how far is a 30 away from the mean of 25? So we calculate the z statistic. So we have to do 30 minus the mean of 25 over the standard deviation, which is 2.5. So now I get 5 over 2.5, which is 2. So now I can look up the probability. So now I use norm.sdist. I want to know the area to the right of 2, so I do -2 and cumulative. And then we get 0.023 roughly, or if we have another one, 0.0228. So this would be 0.0228. So that's the probability that we make a type 1 error. And declaring a healthy person at risk is, well, that's a type 1 error. Type 1 error. So a test that declares a person at risk if the BMI is 30 or greater will identify what percentage of the population correctly as healthy. Well, that is everything to the left now. So that means now if I want to highlight the corresponding area, I will pick up the probability from the healthy, and I copy that down until I reach 30. But now I replace everything after 30 again by NAs. And now this area that you see now, that is specificity, the probability that a healthy person is identified as healthy or a true negative. So a test that declares a person at risk, what percentage? Well, that is equal to 1 minus what we just calculated. So that is 0.997. I decrease what percentage? So that is 0.977. An at-risk person has what probability of falsely declared healthy? Okay, so now let's reset again our areas. So now we look at the risk that a person at risk, which comes from the purple population, is falsely declared as healthy. So that would be a false negative. And that is now from the at-risk population, everything to the left of 30. So I define the area now, everything to the left, but I link it to the at-risk population. So I'll pick up the probability there, and I copy now down those probabilities until I reach 30. And now you see we have the probability that a person at risk is falsely declared not at risk or healthy. So what is this probability? Okay, so now we have to calculate again the corresponding z-score, and the z-score is this time negative. So let's erase this here. So now the probability of making a type 2 error is the z-score of 30 minus the mean of 33 divided by the standard error of 2.5, and now I get negative 3 over 2.5, and that is equal to negative 3 divided over 2.5, so that's negative 1.2. So that means the area to the left of a z-score of negative 1.2 is equal to norm s dot dist. Now the negative 1.2 cumulative. Okay, so this area here, this gray area is 11.5%. Okay, so that is the probability of making a type 2 error, 0.115. So declaring an at-risk person healthy is a type 2 error. Okay, so now the last question is a test that declares a person at risk. That's a typo here. So a test that declares a person at risk if the BMI is 30 or greater will identify what percentage of the at-risk population correctly as at risk, and that is known as sensitivity. Well, this is now everything to the right of 30. So we can go to our area and we put again, so now we have to go and pick up the values to the right of 30. So everything to the left, LNA. So now I go down to 30. Okay. So those are all NAs, but now I want to pick up all the values that are to the right of 30 and coming from the population which is at risk. So I just copy down those values. And this is the area that defines sensitivity, and the probability, of course, is now 1 minus the 11.5, so we do 1 minus. So this probability is 0.885. So the probability that we correctly identify a person who is at risk is 88.5%. And again, a type 1 error is alpha, and specificity is 1 minus alpha. And as we have seen, they need to sum up to 1. The type 2 error is beta, and sensitivity is 1 minus beta, and they also need to sum up to always 1. Okay, so I hope that this is clear how we calculate type 1 errors and type 2 errors, and what kinds of mistakes we can actually do in statistics. Okay, let's stop here, and then let's continue with the next problem set, which is again about a confidence interval and a simple t-test, but let's have a separate video for this one, and I'll just stop here.